We are looking at hypothesis testing, and we start with basics of hypothesis testing. Synopsis of what we covered regarding confidence interval. We looked at confidence interval for proportion, and if you recall, we start with a point estimate, regardless of the type of confidence interval we're looking at. So the point estimate for P, or population proportion, is P hat the sample proportion, where again, P is capital X over N and P hat is lowercase x over N. So P hat plus minus E, that would be the confidence interval. So what is E is called the margin of error, the maximum error, or they call it the error bound. It's Z alpha over 2 square root of P hat Q hat over N. What we need to remember is when we are dealing with proportion, we are dealing with binomial distribution. And when we come up with the Z value, that means we are approximating it with normal distribution. So in the case of a proportion, we only use Z. So when we have the confidence interval, we can evaluate the P hat if in case it's missing, if the confidence interval is given to us because it's smacked in between. Simply put, add up the limits, divide by 2. And if you subtract and divide by 2, it gives you the margin of error. The other thing that we can calculate is the sample size necessary to have the confidence interval within that margin of error. So N is Z squared, P hat Q hat over E squared. It comes from the fact that EZ squared of P hat Q hat over N, we solve for N. And if P hat and Q hat are not known, we can go with the most conservative by taking P hat equals Q hat equals 0.5, and it creates the next formula. Z squared times 0.25 over E squared. As far as the mean is concerned, again, we start with the point estimate of the mean, which is X bar and plus minus E. The same thing, we can find the value of X bar by adding the limits, dividing by 2, or to find the margin of error, subtracting and dividing by 2, assuming the confidence interval is given and we don't have X bar or E. Two things happen. Either sigma is known or sigma is not known. If sigma is known, the margin of error would be Z alpha over 2 sigma over square root of. If that's not the case, then it's T alpha over 2 S over square root of. Now, it's important to know that most of the time sigma is unknown. When sigma is given, we can calculate the value of N Z sigma over E quantity squared, and as always, we round up when we're looking for a sample. When we looked at the standard deviation or variance, we use what's called a chi-square distribution, in which case it's not symmetric and it doesn't go to negative infinity like Z and T. It starts from 0 and it's skewed to the right as degrees of freedom equals N minus 1 gets larger and larger. Then it becomes closer and closer to normal distribution. By that, I mean really it's not a normal distribution, it just becomes more symmetric. Unlike the mean and proportion, we don't start with sample and add and subtract E. It's a different method. It's not symmetric. And therefore, there are different calculations. In this case, sigma squared is between N minus 1 S squared over chi squared of the right and N minus 1 S squared over chi squared of the left. As far as sigma or standard deviation is concerned, all you have to do, take the root. So basics of hypothesis testing. The key concept is that when we are dealing with a formal hypothesis test, the concepts in this section are general and apply to hypothesis test involving proportions, means, standard deviations, or variances. So this is the general idea to get us started, and then we look at each case separately.
Hypothesis. In statistics, a hypothesis is a claim or statement about a property of a population. Hypothesis test. A hypothesis test, or a test of significance, is a procedure for testing a claim about a property of a population.
Researchers are interested in answering many types of questions. For example, is the Earth warming up? Does a new medication lower blood pressure? Does the public prefer a certain color in a new fashion line? Is a new teaching technique better than a traditional one? Do seatbelts reduce the severity of injuries? These types of questions can be addressed through statistical hypothesis testing, which is a decision-making process for evaluating claims about a population.
So there are a lot of applications. Look at this claim and this example.
2,000 consumers were asked if they are comfortable with having drones deliver their purchases, and 54% or 1,080 of them responded with no. Using P to denote the proportion of consumers not comfortable with drone deliveries, the majority claim is equivalent to the claim that the proportion is greater than half, or P is greater than 0.5. The expression P is greater than 0.5 is a symbolic form of the original claim. The claim, the population proportion P is greater than 0.5. Among 1,009 consumers, how many do we need to get a significantly high number who are not comfortable with drone delivery?
So when we read the question, we need to recognize that when we want to set up a hypothesis, and I will give you the steps. One of the steps, the very first one, involves writing the information symbolically, known as the null and alternative hypothesis. As you can see here, if we get 1,020 or 51%, it's just barely more than half. So 1,020 is clearly not significant. We're looking at just the percentage here. The result of 1,900 or 95% is clearly significant. What about 1080 or 54%? Is that significantly high or not? By the way, this is 2,000. So let's just recap. I want to make sure everybody understands what's going on because I thought it was 2,000. There was a typo there. If there are 2,000 consumers and 1,020, which corresponds to 51%, is that significant? As you can see, it's not a lot. It's only 51%. If you look at the second one, clearly 1,900 is significantly high. So the first one, it's close to 50%. It has no bearing. The second one is way up there, so significantly high. The question is, what we really deal with when we have a case like this, what do we mean by that? When it's larger than 0.5, but it's not a lot, maybe 54%, maybe 57%, maybe 61%. How high really shows that it's more than 50%? And we don't know until we test it with statistics. The point being, some are obvious, 1,020 or 1,010 or 1,005, not a big deal. It's close to 50%. And again, by the way, because P is larger than 0.5, we are interested in larger, so we don't discuss something below that. Okay, if it's below 1,000, so it's less than 50%. So the first case and the second case are obvious cases. And that's the idea behind the test of hypothesis. What if it's not obvious? That's what we really do the testing for. Let's see, a statistical hypothesis is a conjecture or assumption about a population parameter. This conjecture may or may not be true. So we have an opinion, an idea, and we are testing it.
The null hypothesis symbolized by H sub O, is that how we say it?
Yes, thank you. H0 or H sub 0, thank you.
Okay, H sub 0 is a statistical hypothesis that states that there is no difference between a parameter and a specific value, or that there is no difference between two parameters.
So it states that the value of a population parameter such as proportion, mean, or standard deviation is equal to some claimed value. So I want to make sure everybody understands what's happening in this case. Now, in some texts, they don't really follow that. They may use also inequality. Most of the time, and most statisticians nowadays follow this, which is what? The null hypothesis, H0, we write it symbolically with the equality sign. It is equal to some sort of a value. So that's the null hypothesis. In some cases, they set up the test of hypothesis such that it's always H0, the null hypothesis, or always H1 or HA, the alternative hypothesis, that is the claim. That's not the case here. We read the question, we make a decision which one is the claim. We discuss that as we come across.
It states that the value of a population parameter, such as proportion, mean, or standard deviation, is equal to some claimed value. The alternative hypothesis, symbolized by H1 or HA or HA, is a statistical hypothesis that states the existence of a difference between a parameter and a specific value, or states that there is a difference between two parameters. It states that the parameter has a value that somehow differs from the null hypothesis, the symbolic form of the alternative hypothesis, less than, greater than, not equal to.
So, number one, notation H0 for the null hypothesis, H1 or HA. A, sometimes they use lower uppercase. A stands for alternative. Sometimes they don't even go with H0 and H1. They just write it, what it refers to. So I want you to see what's happening. When it comes to H0, the equality sign is used. Some texts do not follow that. In the case of alternative, we use one of the inequality signs, less than, greater than, not equal to. That's what we do here. Two-tail test, left tail test, right tail test. So I want you to look at the right side and the graphs. Two-tailed test, as you can see, takes the inequality sign. So this is a two-tailed test. And it takes the inequality sign. And it has two tails. What are the tails? If we go through the process of calculation, and when the procedure is done, we end up with the test that is in those tails, we reject the null hypothesis. Look at the second one and the third one. First of all, both of them are only one tail test. The second one is left tail test, and it uses less than. And the last one, right tail test, uses the symbol greater than. And so what we are looking at, so we have a value here. We have a value here that is separating the middle part, which is an acceptable region, from the tail region, which is the critical region or the region that will be rejected. Here's another one for the left one, and here's another one for the right one. Those are called critical values. So what does the critical value or values do? They separate the two regions, critical regions and non-critical regions.
The critical value CV separates the critical region from the non-critical region. The critical or rejection region is the range of values of the test value that indicates that there is a significant difference and that the null hypothesis should be rejected.
The non-critical or non-rejection region is the range of values of the test value that indicates that the difference was probably due to chance and that the null hypothesis should not be rejected.
And finally,
two-tailed test. The critical region is in the two extreme regions, tails under the curve. Left-tailed test. The critical region is in the extreme left region, tail under the curve. Right-tailed test. The critical region is the extreme right region, tail under the curve.
what do we mean by that? Look at the first one, a two-tailed test. Left and right. Those tails that are just shaded in blue are critical regions. That means when we go through the process, if the test statistic ends up being in one of those regions, we reject H0. Look at the next one. It's on the left side. By definition, we call this a left tail test. So right here. The last one is a right tail test. So basically, wherever the tail is considered to be the critical region. Identify the null and alternative hypotheses.
A researcher is interested in finding out whether a new medication will have a side effect on the pulse rate of the patients who take the medication. Will the pulse rate increase, decrease, or remain unchanged after a patient takes the medication? The researcher knows that the mean pulse rate for the population under study is 80 beats per minute.
So all we want to do is identify the null and alternative hypothesis. Remember, the way we are going to do it here is that the alternative is the one that takes a sign which is not equal, less than, or greater than according. So let's see what we want to find out. In finding, so the researcher knows that the mean, okay, so first I want to look at is this mean. The moment we see mean, that means mu. By the way, the test of hypothesis is only and always about the population parameter, not sample statistics. Why? Because sample statistics, we can just come up with a sample and come up with the sample statistics. It is the population parameter that we are looking for most of the time we don't have access to. It is always about mu. So therefore, you have H0 and H1 involving mu. For the population under study is 80 beats per minute. So that means mu must be 80. That is your H0. Now, what is your H1? Well, it's either less than that, larger than that, or not equal to. So when we go and read further, okay, going back, will the pulse rate increase? That means larger. Decrease, that means less than, or remain unchanged. Because of all of those, that means not equal. So H0, mu is 80. H1 mu is not 80. And this is a two-tailed test. We are just warming up to be able to do a complete test of hypothesis from A to Z.
Invents a chemical to increase the life of an automobile battery. The mean lifetime of the automobile battery without the additive is 34 months.
Now, again, we're looking at the mean, so mu. What is the mean or mu equal to? 34 months. So H0 mu is 34. Going back, rereading the question. A chemist invents a chemical to what? To do what? Increase. That means greater than 34. It's a right tail test. So you read and reread the question, making sure you use the proper notation. It is about the mean, so you use mu. It is supposed to be 34, mu is 34. A chemist wants to say what he's done is going to increase the life of a battery, then it's a right tail test.
A contractor wishes to lower heating bills by using a special type of insulation in houses. If the average of the monthly heating bills is $70, the hypotheses about heating costs with the use of insulation are.
What symbol are we using? Mu. So you're looking for the vocabulary that gives you the symbol. Average, mu. It's supposed to be how much? So mu is
70.
equal to 70. H0, mu equals 70. Now going back, rereading the question, a contractor wishes to lower heating bills. So that means less than. So mu is less than 70. So I hope you see that how we arrive at the very first step. If you have the first step right, you know what population parameter you're dealing with, and then you can easily recognize the formula. And of course, the formula comes from the formula sheet, and the processes are the same. They repeat themselves. So it's important to know this. So the very first thing, what is H0? What is H1? Read and read. Basics of hypothesis testing, 3 methods are used. One of them is called the traditional method. We just looked at the very first step. But what is the process of finishing it off? The next thing is we can find the critical value. So that's known as the critical value method. We already have seen the definition of a critical value, the region for critical and non-critical value, and critical value separates the two. Of course, how do we do that? We will look at that later. But for now, critical value method is one. So what it does, it separates the critical region from the non-critical region. The second one is the p-value method. As far as the specific definition is that the p-value is the probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from the sample data, assuming that the null hypothesis is true. It may be hard to understand the definition, but the idea is the following. In the first case, we compare numbers to make a decision. In the second case, we compare areas. The p-value in essence is the area that represents the area to the right of test statistic for the right tail test, area to the left of test statistic for a left tail test, and of course area to one side times 2 for a two tail test. So we'll see that as we come across. Finally, there is this method of confidence interval. We've already done the confidence interval, and we know how to evaluate the confidence interval, but we're going to see the interpretation when it comes to the test of hypothesis. Because a confidence interval estimate of a population parameter contains the likely values of that parameter, reject a claim that the population parameter has a value that is not included in the confidence interval. And so, again, what does it mean? We will make some sense out of it when we look at examples. The idea is that if the confidence interval contains the value which is for H0, then you do not reject H0. That's the idea, which means the null hypothesis. As far as the equivalency is concerned, a confidence interval estimate of proportion might lead to a conclusion different from that of a hypothesis testing. When it comes to them being equivalent, the first one and the second one are always equivalent. The third one, in the case of a proportion, it's not sometimes, simply because of the formula that we use, they are not the same. Again, it becomes clear as we look at an example involving that. Construct a confidence interval with a confidence level selected. We've already seen the confidence level of 99%, 95%, 90%. It's important that we normally go with those values. Now, corresponding to 99%, and then if you're dealing with a one-tail test or two-tail test, when we look at alpha, which is called the significance level of the test, alpha is considered the significance level of the test. It is also known as the probability of making type 1 error. A two-tail test and a confidence interval, they are complementary. So if you have a 99% confidence level, alpha is 1% for a two-tail test, they are equivalent. 95% is 5%, 90% is 10%. That's very straightforward, I hope. But what if you have one-tail test? Understand the case of a one-tail test. If you have a 99% confidence interval, then it doesn't work with that 1% because that 1% must be on both sides. Now, if we go with a one-tail test, alpha 0.01 corresponds to a confidence level of 98%. Why is that? Because if you have a test of hypothesis alpha is 0.01, you don't want to remember the end points. This is 1 minus alpha, okay, and the tails, each one is alpha over 2. Now again, it becomes clear as we look at some examples. So I don't want you to worry about that too much for now. In some text, it used the original claim to create a null hypothesis H0 and an alternative hypothesis H1. It really depends on the text that you're using. But as I mentioned, there is no limitation. You can, whatever the claim might be H0, might be H1 according to the question that we come across. So we don't want to get bogged down by that.
When a researcher conducts a study, he or she is generally looking for evidence to support a claim. A claim can be stated as either the null hypothesis or the alternative hypothesis.
And that's really the idea here. Some authors and some texts specifically go for one. But over here, either way is fine. We don't have to force the claim to be the null or alternative hypothesis. It is what it is. So it could be the null, could be the alternative. We'll see.
After stating the hypothesis, the researcher's next step is to design the study. A, the researcher selects the correct statistical test, such as Z, T, or X squared. B, chooses an appropriate level of significance and formulates a plan for conducting the study. C, critical value method, P-value method, confidence interval method.
The idea is that the test statistic that we need to calculate, it really depends on the nature of the question. Does it pertain to proportion, mean, standard deviation, or variance? And accordingly, you make a decision what to use. And as far as the alpha, normally it's given to you. If you are the researcher, you make a decision what alpha should be. Now, alpha in most researches is equal to 0.05. Normally, remember, that's good enough. The concept of 95%, the usual. But when it comes to medicine, for example, then you want to be more careful. So it's more extreme. So 0.01 maybe, or 0.001 for that matter. And so when we have the plan, we go with the critical CV, short for the critical value method, P-value method, CI, or confidence interval method.
A statistical test uses the data obtained from a sample to make a decision about whether the null hypothesis should be rejected. The numerical value obtained from a statistical test is called test statistic, or value. The null hypothesis may or may not be true, and a decision is made to reject or not to reject it on the basis of the data obtained from the sample.
So the idea is this: we go through the process, and the process involves the very first step we've already discussed, H0 and H1, and then some calculations. The calculations, they involve one of those methods, the critical value method, the P-value method, the confidence interval. And so with that in mind, we come up with a statistical test, which again depends on the nature of the question, whether it's dealing with a proportion, mean, or standard deviation or variance. You calculate that, then you compare, and you make a decision. Your decision has really a few parts, but the very first part and the most important part that has got to do with your calculation is that the null hypothesis, H0, may or may not be true, and a decision is made to reject or not to reject. So the very first step is rejecting or not rejecting H0. Here's an example. Finding the critical value for alpha equals 0.01 for a right tail test, left tail test, and a two tail test. Anytime we want to do that, this is using a specifically Z table that we've been told. Anytime we want to do that, you want to come up with the graph. So if you're looking at part A, alpha is 0.01 and it is right tail test. Graph it. So the right tail contains the area of 0.01, and that's the critical region. That's the rejection region. And the rest of it, 1 minus 0.01, is on the left side. Now, all you have to do, find this Z value from the table. Looking at a table, you want to go for the positive Z score, and you want in the Z table, in the body of the Z table, you're looking at 0.01 on the right. That means 0.99 on the left. And you want to look up the Z. I give you the answer, then I expect you to work on it a little bit to make sure you're comfortable with the table. So Z becomes 2.33. 2.33 may not be there. You may have to go somewhere in between. I'll discuss that with the table in a moment. For the next one, now the critical value is the same thing, but it's left tail test. So it looks almost identical on the left side. Now, if I have the answer for part A, do I have to look up the answer for part B, or can I come up with that on my own now? No, why not? And what is the answer?
It's going to be the negative.
And the reason why, because of symmetry. If I have the answer for part A, I don't waste my time. I just quickly write the answer for part B as negative 2.33. Now, when you look at the last part, now you have 0.01. We want to find the critical value for alpha 0.01, but it happened to be two-tailed test. What does it mean? It means 0.01 divided by 2 goes on each side. So each side has 0.005. So you go to the Z table and you look at the body of the table, not the left column, not the top row. And you look for the area equal to 0.005. And it gives you negative 2.575. It's one of those common values. Then the positive one is the same thing, positive. So plus minus 2.575. Now, I want to discuss this concept of a confidence interval here. And then the next page, you can look up the table and we discuss the table. But if you are dealing with the first two cases, alpha is 0.01. These two cases correspond to confidence level of 98%, not 99%. Why not? Why? Because confidence interval is smacked in between. So it is the middle that is 98%. And so you have another 1% on this left and another 1% on this right. So A and B, alpha equals 0.01, they are one-tailed test. So 0.01 alpha corresponds to 98%, not 1 minus 0.01. However, if you look at this one, now this is corresponding to 1 minus 0.01 or 99% confidence level. So that's important to realize. Now, I want to discuss using the table and how we use it to get to the answer. So here's the next example. I'm going to give everybody a chance to come up with the answer. I want you to look up the table. So we want a left tail test to be alpha 0.1. That means this area is 0.1 and you need to look up the table. I will show you the answer, then we go to the table. I want to show you the answer for all of this first. So the left is the region which is known as a critical region or rejection region. We end up with negative 1.28. For a two-tailed test, alpha is 0.02. It's not to scale, it's just to give you an idea. You have two tails, so each one is 0.01. 0.02 divided by 2. And you look up the table and you end up with plus minus 2.33. Finally, a right tail test, 0.005. So that's the right tail test. And we look up the Z table. If we look up the table, we might see 2.58, but we pay more attention and we see 2.575. I want to quickly show you how this thing works with the table. Let's discuss the first one. We said a left tail test with alpha 0.1. We want the area to the left. So I'm looking at negative z squared. So we want the area to the left to be 0.1. So what it means that you look up the body, not the left column, not the top row. You look for the number which is identical to 0.1 or very close to 0.1. So in this area, the body, we are looking for number 0.1. Notice if we look at this number, so let me bring it up again. So this number is close to 0.1, 0.10, and so negative 1.2, negative 1.2. You're here. This number is close. This number is close. See, I'm moving to the right. So I found negative 1.2. That would be a good choice. And as we move to the right, notice what happens. This one is the closest, 0.1003, and then 0.0985. This is the number looking at, and then look at this one. I put a dot next to both of them. So it's really 0.1003, which is the closest. But if you went in between, it's fine. So if I'm looking at 0.1003, I'm reading negative 1.28. Negative 1.28, because this is negative 1.2 and this is 0.08. So that's how we do the read. Now, if you look at the next one, the next one says a two-tailed test. Alpha is 0.02 class. A two-tailed test, alpha is 0.02, which means each tail contains 0.01 of area, 0.01. Now, going back to the table, we want to look in the body for 0.0. As we look for it, for 0.01, you see that we are somewhere here. So I want you to see that, this number and this number. Look at those two dots. So I'm looking at this one and this one, okay? Now, the first one is what? Negative 2.32, and the next one is negative 0.233. The second one happened to be close, but honestly, I would actually write plus minus 2.3 and in between 2.5. I'll put it up for you in a moment. We do the reading in this manner. We look at the body of the table, because this is the part sometimes students have a difficulty. And the last question on this page, this is the one. It's asking a right tail test with alpha of 0.005. So the right tail test is 0.005. It's the same as the left tail test being 0.005, and then you negate that, or you can go to the pause. It really makes no difference as long as you are comfortable with the concept of symmetry. So with that being the case, so take a look and see what happens. We want 0.005, so we have this number. Okay, I'm going to put next to 0.0051, and then this number 0.0049. Okay, now so that means negative 2.5 and then 2.57, between 7 and 8. Now take a look. In fact, I want you to look at this arrow. Look at this arrow, and let's come down. See, because it's one of those common numbers we come across, it's given to us negative 2.575. Now, because this is negative 2.575, this must be positive 2.575. And we have the answer. For this one, plus minus 2.33, I would use the number in between as it was discussed. I would use plus minus 2.325. As I mentioned, this is the one. If you go back to the table, I would choose plus minus 2.325. That's closer class in between, unless it's completely closer to one side. Let's type 1 error.
Type 1 error. The mistake of rejecting the null hypothesis when it is actually true. The symbol alpha is used to represent the probability of a type 1 error. A type 1 error occurs if one rejects the null hypothesis when it is true.
Rejecting the true null hypothesis, in short.
The level of significance is the maximum probability of committing a type 1 error. Alpha is equal to P type 1 error is equal to P rejecting H sub 0 when H sub 0 is true. And typical significance levels are 0.1, 0.05, and 0.01. For example, when alpha is equal to 0.1, there is a 10% chance of rejecting a true null hypothesis.
Thanks. I hope everybody understands what we are trying to do. First, concept of alpha, what it means. It is equal to the probability of making type 1 error. Type 1 error is defined as rejecting the true null hypothesis. And when you choose alpha, what it means. In this case, if alpha is 0.1, then there's a 10% chance of rejecting a true null hypothesis. And that's why alpha, normally researchers pick it accordingly. It depends on what the situation is. And in most cases, as I said, it's 0.05. If you're looking at situations that are more critical, you want to make that small. Type 2 error.
Type 2 error. The mistake of failing to reject the null hypothesis when it is actually false. The symbol beta is used to represent the probability of a type 2 error. A type 2 error occurs if one does not reject the null hypothesis when it is false. Beta is equal to P type 2 error, P failing to reject H0 when H0 is false.
So again, we really want to distinguish between the two. First of all, the probability of type 1 error, we say alpha is equal to alpha, the probability of rejecting the probability of type 2 error. That means failing to reject H0 when it's actually false. And that is beta. I want to make sure everybody understands. When the null hypothesis is true, we shouldn't reject it. If we do, we are making a mistake. That's type 1 error. If it's not true, we should reject it. And if we don't reject it, we are making a mistake. That's called type 2 error, and that's equal to beta. 1 minus alpha is the confidence level, and 1 minus beta is called the power of the test. So we have the table here explaining the whole thing as far as type 1 error, type 2 error, the making the correct decision, confidence level in essence. So rejecting H0 and failing to reject H0, it explains here as to what's going on. So rejecting H0 when null hypothesis is true, we are dealing with. So rejecting when the null hypothesis is true is the type 1 error. Whereas fail to reject H0 when the null hypothesis is false. Please, describing type 1 and type 2 error, example 5.
Consider the claim that a medical procedure designed to increase the likelihood of a baby girl is effective so that the probability of a baby girl is p greater than 0.5. Given the following null and alternative hypothesis, write statements describing A, a type 1 error, and B, a type 2 error. Hint for describing type 1 and type 2 errors. Descriptions of a type 1 error and a type 2 error refer to the null hypothesis being true or false. But when wording a statement representing a type 1 error or a type 2 error, be sure that the conclusion addresses the original claim, which may or may not be the null hypothesis. H0 p equals 0.5, H1 p greater than 0.5, original claim that will be addressed in the final conclusion.
With the test of hypothesis, symbolically we represent H0 and H1, and then for the explanation we can do the right. So what would be type 1 error? Remember, what is type 1 error? Rejecting the true null hypothesis. So with that being the case, we should be able to recognize the type 1 error.
A type 1 error is the mistake of rejecting a true null hypothesis, so the following is a type 1 error. In reality, p is equal to 0.5, but sample evidence leads us to conclude that p is greater than 0.5. In this case, a type 1 error is to conclude that the medical procedure is effective when in reality it has no effect.
Remember the meaning of type 1 error and discuss that symbolically, and then put it into words. So rejecting a true null hypothesis. A null hypothesis says p is 0.5, but if we reject that, and remember, we reject it based on the data, okay, sample data we pick. So that would be type 1 error. Now, what does it mean in words? A type 1 error is to conclude that the medical procedure is effective. That means p is larger than 0.5. Then in reality, it has no effect. And here's type 2 error.
Type 2 error is the mistake of failing to reject the null hypothesis when it is false, so the following is a type 2 error. In reality, p is greater than 0.5, but we fail to support that conclusion. In this case, a type 2 error is to conclude that the medical procedure has no effect, when in reality it is effective in increasing the likelihood of a baby girl.
What is type 2 error? When we fail to reject the null hypothesis when it's actually false. So first, remember this definition. Use the fact H0p equals 0.5, H1p is larger than 0.5. Answer that accordingly, and then do the writing. So a type 2 error is to conclude that the medical procedure has no effect when it actually does. That's the idea behind type 1 and type 2 error. So to answer the question for type 1 and type 2 error, first I would write the meaning of it, a shorthand notation as to what it means, then symbolically, and then in word. A procedure for hypothesis test There are really three procedures: critical value, p-value, and the confidence interval. We've already seen that. So when we do that, the very first step is to come up with the null and alternative hypothesis class. You write down H0, you write down H1. Same thing for the p-value, it makes no difference. The next one is to calculate the TS, short for test statistic. Now that means you can calculate the Z, T, or chi-square, and there's the same thing happens with the p-value. Now what is the next step? In the case of a critical value, you come up with the graph using the table. You find the critical values and you do the drawing. In the case of a p-value, you look at area to the right of test statistic if it's right tail test, to the left of it if it's left tail test, and if it's two tail test, whatever the test statistic on any side, you come up with the area of that side, you multiply by 2. So the p-value is the area. The critical value is just a number. And now you compare steps 2 and 3, and you make a decision in the case of a critical value, which means the value of test statistic calculated is either in the rejection region, that means is one of the tails, and you are going to reject H0, or it's not, in which case you're going to write the following. The last step is making a decision. What is your decision? Reject or not reject the null hypothesis. Actually, they write down fail to reject. If you want to be very specific, write reject or fail to reject. That's one part. The next part is that you write, okay, now that you've made that decision, the claim is either true or false. You make a note of that. And then finally, you restate the decision by writing there is or there is not sufficient evidence to support the claim that, and you just write the claim that is given. So you either support it or you don't based on your calculations. When it comes to the p-value, you do exactly the same thing. As far as the decision making is identical. The only thing is you compare the p-value, which is the area, to alpha. So p-value is compared to alpha. If it's larger than that, you don't reject H0. If it's less than that, you do reject H0. Now, there is an example that I want to go over, and actually, in essence, class, we are moving towards the next section. So I'm going to do that example here because we want to discuss the p-value and everything, and that's good enough. We will come across the same question in the next section, but it is worth looking at it twice, but when we do that next time, we do it fairly fast. So let's look at a simple example.
1,009 consumers were asked if they are comfortable with having drones deliver their purchases, and 54% or 545 of them responded with no. Use these results to test the claim that most consumers are uncomfortable with drone deliveries. We interpret most to mean more than half or greater than 0.5. Alpha equals 0.05.
If you look at the top right in blue, that is the test statistic for proportion Z equals P hat minus P over square root of PQ over. What we need to realize is that either you're comfortable or uncomfortable. So that means yes or no. That means a proportion. That means a binomial distribution. Now, because you see even the formula Z, that means you're going to go with the Z table. That means you're going to approximate the binomial distribution by normal distribution, and therefore you want to check whether it's doable or not. So let's write what is given. So 1,009, that's N. For those 1,009, you want to see what's given, 54%. And we are given P equals 0.5. Remember that, it's mentioned here. So you are going to look at NP and NQ, making sure it's large. So we are dealing with a binomial distribution. N is 1,009, P is 0.5. By the way, the Q will be calculated as 1 minus P. Everybody knows that. NP and NQ are large. Okay, so we use normal distribution. And X is 545. So that's what they give us. Look at the very first step. Step 1, state H0 and H1. H0, you always use equality. Therefore, you are going to use H0 P equals 0.5. What about H1? Well, what are we testing? Test the claim that most, now, greater than or larger than makes it right tail test, and it is the claim. So I want you to see the importance of writing the first step properly. Number one, you know which population parameter you're dealing with. Number two, you realize it's right tail test or left tail test or two tail test. Okay. And number three, you would write the claim next to H0 or H1 accordingly. And I hope you see that in this step, it is H1 that is the claim. All right. Step 2 is calculating test statistic. Look at the top formula. You have to use that to calculate that. And we already have p hat equals 0.54. But if we stick with 545 is not, yeah, you can calculate it and it becomes about 0.54. Now using this step, test statistic is p hat. You want to make sure you can access that and find out where the formula is in your formula sheet. And so p hat 0.54 minus p, which is 0.5, okay, divided by square root of pq. What is p? 0.5. What is q? 0.5. Divided by n. What is n? 1009. So this is the formula. And 2.55. All right. Your next step, finding the critical value. Look at step 3, CV short for the critical value. We are using the Z table. Alpha is 0.05. That means really for the third step, we do the drawing of the Z table roughly. We said, going back here to the first step, right tail test. That's what we want. And we look up the Z table. And that gives us positive 1.645. The next step is to make a decision. Now, when you want to make a decision, your data gives you the very first one, A, reject or not reject H0. I want everybody to pay attention to this. This is the one we are going to answer, and then we're going to elaborate. How do we answer that? If you compare this, so this is 1.645. What is my test statistic? 255, okay? Now 255, I hope you see it's larger than 1.645. And it doesn't have to be to scale, it's somewhere here. It's way into the tail, into the rejection region. Look at this. Critical value is 1.645 and the Z is 2.55, way into the rejection region. So what do? Reject H0. So I want to make sure everybody understands what happens next. If you are rejecting H0, that means you're accepting the claim. So you are not rejecting H1. You are accepting H1. That means the claim is true. And then you do the writing. So reject H0. All of your calculation is about this part only. This is the part that comes from your calculation. And now you do the writing. The claim is true because it's sitting not next to H0, rather H1. And therefore, there is sufficient evidence to support the claim that the majority of consumers are uncomfortable with drone deliveries. The writing comes from here. You just write it, just the way it is. And the way you write it is, there is sufficient evidence to support the claim, or there is not sufficient evidence to support the claim, and then you write from here. In this case, when we do the test of hypothesis, when we want to calculate the test statistic, It depends on what we are dealing with. Proportion, mu, sigma, or sigma squared. So we use this column known as test statistic. All of them are available to you. So if you're dealing with a proportion, your C is p hat minus p over square root of pq over. If you're using with mean, mu depends on whether sigma is known or not. If it's known, z is x bar minus mu over sigma over square root of n. And if it's not, you use the t. Finally, if you're using standard deviation or variance, then chi-squared is n minus 1 s squared over sigma squared. Let's look at the concept of a p-value as explained here. So take a look at the idea of a p-value. It's either left tail test or right tail test or two tail test. If it's left tail test, area to the left of test statistic. That's your p-value. If it's right tail test, to the right of that. If it's a two-tail test, then when you calculate the test statistic, it could happen to the left or right of 0. So the area to the left of that, then times 2, or to the right of that, times 2. So when we go back to our question, remember the test statistic was 2.55. So this was test statistic, Z. So by definition, is the area to the right of it. And you compare that with alpha. The choice of alpha in that question was 0.05. If this one is larger than alpha, that means you're way into non-rejection region. If it's smaller, then you're into rejection region. So if it's smaller than p-value, you reject it. You reject H0. If it's not, you don't. So test statistic was 2.55. It was a right tail test, and we can come up with the z larger than 2.55 from the table, technology, you name it, and we end up with 0.0054. And it is clearly less than alpha of 0.05. So here's the decision criteria. If p-value is less than or equal to alpha, we reject. In other words, reject H0. If the P is low, then no must go. That's one way perhaps to remember. If the p-value is larger than alpha, fail to reject H0. I want to make sure everyone understands what's happening here. And that is, when you are looking at alpha, remember, if we go back to the critical value, okay, CV, Z was equal to 1.645, and this alpha was 0.05. The area is smaller. That means the critical value is in the rejection. The test statistic is in the rejection region, and therefore you reject H3. Finally, we don't want to mix up the p-value. Okay, let's look at the very bottom. P-value is the probability of a test statistic at least as extreme as the one obtained. In other words, p-value versus p itself, which is a population proportion. P hat, sample proportion. So we really don't want to mix them up.